Okay, so maybe we can start just with a short recap of what we have discussed so far. So we are looking for this decay, and we are trying to design an experiment. We identified the signature that we want to be able to highlight in our experiment, that is the sum energy of the two electrons, which is monochromatic, and it should appear in the spectrum of events at the transition energy. Then we have discussed the kind of candidates, and we have identified nuclei with either a high isotopic abundance, or in any case with that can be enriched. And we have seen that given the present results, in order to have sensitivity for our experiment that want to go beyond the present achievements, we have to be able to explore half-life that are longer than 10 to the 26 years. And this will require a 1-ton detector, a 1-ton source, that means 1 ton of isotope. And since the double beta decay is is an event that where the two electrons that we want to detect have a very short range, something like 2 millimeters in a solid state material. We need that the source is itself also the detector of the events. And we have discussed of, and we are still discussing of the possible sources of background. The first one, and we have defined the background. Background is any event that can be detected by our detector as having an energy equal to the transition energy of neutrinoless double beta decay. So an event that in principle I'm not able to distinguish from a good event for my research. And one irreducible background is the tail of the two neutrino double beta decay. And there is no way to distinguish this background from the neutrinoless, because the only difference is that two neutrinos are emitted. I have no chance of detecting the two neutrinos. Everything else is identical. That's not true. What can change? What can change is the single energy distribution. Okay, so what we have discussed is the first source of background that are muons. And what I've told you is that we can build a veto surrounding, okay, I go on the ground because I want to remove all the background induced by cosmic rays. I go underground. Underground, I still have muons. And to avoid, to reject events that are induced by muons and produce counts over here, what I can do is to build a veto surrounding my detector and then tag events that can be induced by muons. And I told you that one background that where the muon veto could be a bit inefficient the one, I mean, is when a muon produces a metastable nucleus. And for sure, Riccardo will discuss this. Riccardo Bruniera discussing legend. Maybe I will not able to come back to this background source, but keep this in mind. Now we have neutrons. Assume I am already underground. Okay, so because I know from muon-induced background that I have to be over there. What are the sources of neutrons underground? First question. And what is the energy spectrum of these, let's call environmental neutrons? And how can I mean, do they produce, are they able to mimic a double beta decay event? And how can I get rid of this background? So let's start from the sources. Have you any idea of what produce? I mean, neutrons, of course, need to be produced by some interaction. Have you any idea of what? Okay. We have one of the source is yes, and alpha is this one. Are you familiar with this way of writing an interaction? So this means that I have a nucleus, and this interacts with an alpha particle, and the products are a nucleus and a neutron. And this kind of interaction takes place every time I have alpha particles, and alpha particles are produced by nuclear decay, and natural radioactivity is a source of alpha particles. Okay, so this is a process that produces neutrons. When I am underground, this process takes place inside the rock, because the rock is, of course, the rock of the mountain is contaminated in uranium and thorium. Uranium and thorium, in their decay chain, have several nuclei that produce alpha particles, more or less of 5 MeV, and they can induce this reaction. Of course, this reaction is a very small cross-section, but the rock is huge. And stopping a neutron is not easy. Therefore, you have a large volume where a neutron can be produced inside the mountains, and they are emitted and they reach the cavern, your tunnel, and your underground hole. Then, any other? Yeah. We have also spontaneous fission of uranium. Again, is the natural content of the rock. And then I have a third source. Sorry? From muons. Yeah. Muons, as I told you, muons can produce metal-stable nuclei with different processes, including the production of a muon. And later the neutron is produce a metastable nucleus. So I have these three possible sources, and keep in mind these sources I've described them as a mechanism from neutron production inside the rock of the mountain. But the same free processes can take place in the infrastructure and in my detector. Okay? Sorry? I cannot hear. Neutrino. Se parlate, if you speak all together? An atmospheric neutrino. I mean, atmospheric neutrinos generally they produce muons. I mean, and then yeah, of course, but you are I mean, if you think that the process that you have atmosphere or whatever neutrino, whatever the source, produces a muons, and afterwards the muons produce a neutron. Of course, this can take place, but the amount of muons produced by atmospheric or solar neutrinos is quite small if you compare with the residual muon flux, so it's not a dominating mechanism. And then, of course, you can have a lot of, you can think to a number of different processes that can produce neutrons, but these are definitely the dominant one, because you see, I mean, muons have still a non-negligible flux on the ground. And these two processes, they are both, I mean, the cross-section is quite small, but the source is the rock that is huge. And there what is important is that neutrons are not easy to stop. Okay, so you can have a very large volume that contributes. And underground, what you get from cosmic rays is just, yes, neutrinos, but for for neutrinos, the Earth is more or less transparent, okay? And so the amount of neutrino conversion inside the Earth is very, really a rare process. So what is the spectrum of these free sources? Okay, mainly these two sources produce neutrons that can have energies up to 6-10 MeVs. And then neutrons produced by muons can have even higher energies. But of course, neutrons interact in the rock and in everything that is inside the underground lab. And so what you get is a degradation of the spectrum. So even if at the beginning these neutrons have a rather high energy, you have when you look at the environmental neutron flux underground, but it's the same also at sea level, you see a lot of thermal neutrons. And what you need to know is that since neutron interaction is very special, quite different from the interaction of all the other particles, it's also very difficult to measure the neutron flux. And here I have summarized, they are not all the measurements that are viable underground, but at Gran Sasso, but more or less they are here. This is a collection of rather old measurements that were done starting from the first, I mean, the older one was done for the neutrino solar neutrino experiment named GALEX. And you see that this is the width of the energy bin that was defined by the measurement. And you see that in some cases they are very wide. And this is a more recent spectrum. So keep in mind that this is logarithmic, while this is linear. So more or less what you are seeing here is basically this 2 or 3 bins here. And this is the region of what we call thermal neutrons. And then we call them, when the energy increases, epithermal, and then we have fast neutrons. Fast neutrons are those that we discussed at the beginning as an example of particles that can induce a nuclear recoil, like a WIMP. And so the point is, how do lose energy neutrons? How do neutrons lose energy when interacting with matter? And how we can detect them? Because we already established that it is true that a neutron can produce a recoil, like in this case, but it's not easy to detect that the recoil. And on the average, I mean, neutrons like those with this spectrum can lose energy with recoils that have of the order of 10 keV. That is a small fraction of their energy. So first, what is the better target to induce an energy transfer to a nucleus? It's a light target, because the energy transfer is optimized when you have the light target. So the lightest target is hydrogen. And so this is a good way to, we call it thermalize neutrons. So but in that case, I'm not able to measure them, okay? Because I do not, I mean, unless I use a dark matter detector to measure, that is something that is done, but only recently, to measure the neutron flux, I'm not able to see these, to measure, to see neutrons and measure their flux through this process. How can I count neutrons then? I need to use a different process. What are the processes that neutrons can undergo when interacting with matter, producing, at the end, I mean, the technique should be a neutron interacts with a nucleus or an electron, as you prefer, as you think it's possible, and produce a signal that I can detect with some device. Okay, of course, a neutron interacts with a nucleus and not with an electron. And let me write this interaction as we generally do. Okay, one kind of interaction is this one. Okay? A neutron hits a nucleus, produce change the status of this nucleus and produce a gamma rays. So this is a different nucleus, and then I have a gamma rays, okay? And I can have the same, for example, for an alpha particle. And then I can have something like this. Okay, and these are different nuclei. Okay, I can write a list of different possible interaction of the nucleus. The main problem is that if I plot the cross-section, it's something like this. This is the energy of the nucleus, or the neutrons, and this is the cross-section. So the cross-section decreases with energy. So when I have, and then there are resonances, and you can have high peaks at specific energies. So this free mechanism produces mainly high energy neutrons, not thermal neutrons. When these neutrons interact with matter at the beginning, this cross-section, that is the inelastic cross-section, is very small. And so they lose energy only through the elastic scattering. And they need to do a lot of scattering to see their energy decreased enough to interact with one of these interaction, mainly in this region. And this process we call thermalization, okay? So a neutron undergo thermalization, and when it is thermal, more or less, or interaction, inelastic interaction starts to be important. And this is also the interaction that produces background in my mimic double beta decay, because of course here we decided that our candidate has a transition energy of 2 MeV, so a neutron cannot produce a nuclear recoil of 2 MeV. So when they are high energy neutrons, they are not, their background, the induced background is not that important. But when they become thermal, they can produce interaction that, producing particles that can be dangerous. There is an additional mechanism with which neutrons can produce interaction that are dangerous. That is the creation of, they can produce metastable nuclei. And this can be done also when they have high energy through a process that is called spallation. That can take place also with muons. You have a nucleus that is, in the interaction is split in 2 parts. And this can be also as well dangerous as this, the others. So here you see an example of the cross-section. This is the cross-section, I think, until, I'm not sure, maybe it is on germanium, because yes, probably, I don't remember. There is a database online from the National Institute of Standards in the US where you can download all the cross-sections. So I don't remember if I downloaded that of germanium or that of tellurium, but in any case, it's just to give you an idea. So an example of production of metastable states from neutrons is that of germanium-77, is an interaction of germanium-76. And as an example of spallation production, this is an interaction that takes place with fast neutrons, so high energy fast neutrons. One example is the spallation production of tellurium with the production of cobalt-60. So tellurium the double beta decay candidate is mass 130. So you basically split it in two parts. And we studied this interaction because cobalt can produce a line, a gamma line, which is quite close to the double beta decay peak of tellurium. So this is an example of neutron-induced background through a metastable state, that of cobalt, that is a long-lived isotope produced by neutrons. Now, that is not a spectrum, that is a cross-section. Yes, of course. So generally what you do is you need a Monte Carlo simulation. You simulated the flux. Okay, when you design a double beta decay experiment, as in the case of most experiments, double beta decay, Monte Carlo simulation are quite important. So you need input for the simulation that is the neutron flux. Okay, you design you introduce the geometry in the simulation of your apparatus. You need a database with all these cross sections so that in the simulation you can produce all these nuclei and these events. And then you propagate these particles down to interaction in your detector, and you get the background. So of course, you can predict more. In principle, you can predict very well the induced background. The point is that you need to know very well all the cross sections. And this is easy when you consider a special for thermal neutrons. You know very well the cross sections because they have been studied for nuclear reactors. The case where it's not easy to know the cross section, in general, I mean, not only for thermal neutrons, but for all these processes, you have evaluation of the cross section. If you want to evaluate the cross section of for spallation, you have theoretical evaluation of that, and there is a kind of phenomenological approach that provides you a cross section that you have to add to your code. Generally, is not. For example, GEANT does not include that, and then Monte Carlo is always reliable when you have very good inputs. So the main problem here is the inputs. For example, if you want to know what we have done for tellurium 130 is that at the beginning we relied on the cross-section. Is a historical paper. The author are Silberberg and Tao. But there was a mistake in there. And so the production, we were very worried because there was a high production, I mean, on the basis of calculation, I mean, the mistake was in a code that based on that paper was used to evaluate the amount of cobalt-60 produced by tellurium, spallation in tellurium, and it looked very dangerous for our experiment. And then we made the measurement. So what we have done is you place a sample of material on a neutron or proton beam, because at a very high energy, nucleons have more or less the same behavior. So it's not important if it is a proton or a neutron. There are beams available that more or less reproduce the beam of, I mean, the energy distribution of nucleons in the cosmic rays. You place there your sample for a while, and this is activated. And then you put it on, typically on a germanium detector, and you detect gamma rays. And in this way, you understand which are the metastable nuclei that have been produced in the sample. And there is a problem over there, because in double beta decay, you are worried not but by the metastable isotope that decay, have a fast decay, but by those that are that have a very long half-life, as it is the case of 60 that has a 5 years half-life. And so to have sensitivity, you have to store for a while your sample after activation, and then wait for, it's called cooling down, and all the fast isotope decay, and then you measure and have sensitivity for that. Okay? So at the end, you are able to I mean, to have prediction, but the problem is to have a very good control on the inputs to really rely on these predictions. Oh, sorry. Oh. Okay, so we know what is the interaction. We know that neutrons are dangerous. They exist at the ground and they are dangerous for our experiment. And the problem is that we cannot use for the rejection of neutrons induced background the same technique that we used for muons, exactly because of the kind of interaction they have. We cannot track a neutron and say it is, we have a neutron there at this time, and then we say open a gate, and for a while we do not accept event because they could have been produced by the neutrons. So the main technique that is used is that of having passive shields. The muon veto, for example, if you have a Cherenkov scintillator, can be also a good system to thermalize neutrons. Okay, but at the beginning, what you mainly need to do is to thermalize neutrons so that once they are thermalized, they interact, and you can either tag them because they interact, or you can capture them and remove from your background. So, for example, the solution adopted, this is Cuore, and you see, I mean, the detector is an array of solid state detector here in the core. This is a cryostat to cool down this array. And the strategy for the reduction of neutrons is to have a shield of polyethylene. Polyethylene is a material that contains a lot of hydrogen, therefore is a very good thermalizer. And then in between, here there is also a lead shield. And in between polyethylene and lead, we have some boron, because boron is a nucleus that undergo neutron capture with a mainly emission of alpha particles here, and the recoiling lithium atom, but a very small low energy gamma. Because you see the point. I want to use one of these reaction once first I thermalize, so I move my neutron from here to here. Then I want to have an interaction. In this case, should be a passive system, so I do not have any detector that will tell me there is a neutron here. I just want to remove the neutron so that it doesn't enter in the region where I have my detector. But I do not want to produce an additional background, okay? So this reaction is not nice because produces gammas. For example, we have nuclei that can capture neutrons with a very high cross-section but produce a lot of gammas. Boron is very good because yes, it produces some gammas, but at very low energy. They are not dangerous for my experiment. Well, what is the range of an alpha particle? And it is in between the lead shield and the polyethylene, so it stopped there, the alpha. Of course, the alpha? Yeah, of course. I could have also, no, okay. I mean, I have boron here. The neutron reacts on boron and produces the alpha particle. Then what could be the danger is that this alpha particle could interact on and produce on a nucleus and produce a neutron. That is what could be dangerous. Yes, this is true, and for this reason, but not only for this reason, all the material in here have a very low neutron cross-section. So you try to avoid that those neutrons are those neutrons are dangerous. And in any case, keep in mind that I mean, it's like a second-order process because you already reduced a lot your neutron flux, and you are discussing of a process, the alpha n process that produce neutrons from alpha particle that has a very low cross section. This is important in the rock because the rock is a huge volume, is less important in this case. So of course it's just a balance of everything, but it's something that you need to take under control. But I think that we are discussing of two rare processes, and therefore you have the product of their probability, and so it's nearly negligible. And then depend on the level of your background. So the final step is gammas. When I'm underground, I still have environmental gammas. And here is I mean, it's just a representative spectrum of what you could see if you measure environmental gammas either underground or above ground. You have a continuum decreasing in energy due to cosmic rays, and you also will see in whatever detector also a peak due to muons that those muons that produce ionization in your detector. But basically your gamma spectrum will be something like this, plus a number of peaks that are due to the radioactive chains. Okay? So basically, underground, we have gammas. If you want to know the sources are mainly radioactive chains, plus a number of other, maybe it's I forgot. Sorry. Plus a number of other sources. And this is an example of a measurement done underground. Okay, the previous one was what I measure with, say, a germanium detector above ground. Then when I am underground, I reduce very much this peak. Note that the position of this peak depends on, can you guess? The position in energy of this peak in any detector is different. Is the size of the detector, okay? Because it depends, I mean, it's just geometry. Is the minimum ionizing, since a moon is a minimum ionizing particle, the amount of energy that deposits inside the detector depends from the constant, the energy deposited per unit length, times the length of the track of the particle. So the length of the track of the particle depends on one direction that, for example, if I am underground, they come, mainly from above. If I am on a flat surface at sea level, they can come on 2 pi, from 2 pi. And then the geometry of the detector. When I go underground, they are much reduced, and this is the spectrum that we measure. For example, this was collected in Oley and at Gran Sasso, so you see this decreasing flux with peaks. Peaks correspond to the gamma line of environmental radioactivity. And keep in mind, this is not the flux. This is what we measure with a detector. So it's a flux folded with the efficiency of your detector. Okay. This is the region of where populated by the double beta decay signal of the best candidates that we discussed today. And so the problem are, the background due to, mainly the background is due to the lines, okay? Look at this line. This background is due to what is coming from this line? Compton, yes, mainly Compton, okay? So how we can get rid of that background? But again, you need the shield. Again, because gammas are not tracking the I mean, they are not their behavior, their way of losing energy is not similar to that of muons, but from this point of view, they are more similar to that of neutrons. It's not easy to track them. You can use a passive shield or a very large volume shield where they can interact and deposit active shield like a Cherenkov detector. And you can use lead, for example. Again, this is a case of cryostat. In connection with this, let me give you a few information background reduction. Okay, these are 3 different implementation of double beta decay experiments. This is Cuore, I've already shown you. This is the cryostat. This is the system of shields, lead and polyethylene. It can be moved up and down. This because when you mount the detector in the cryostat, you have to remove these shields and work over there. And then you move it up when you are running. So this is an experiment that uses only passive shields. And at present, Cuore even doesn't have a muon veto because muon background is negligible in the present experiment. This is Legend 1000, so it's not yet built, but Legend 200 is not very different, and uses a Cherenkov, water Cherenkov veto, and then have liquid argon inside to cool down the germanium detectors. And all these liquids act both as passive shields, they absorb radiation, but they also provide signals that can be used to veto them. And similar, this is Camland-Zen. Camland use the Camland infrastructure. This is the experiment that claimed for neutrino oscillation. The isotope is inside this balloon. Now there is a liquid scintillator in here, a water Cherenkov outside. So the structure overall is quite similar to that. Yeah. Yeah. Okay. Okay, so you understood the question. The veto is used to, I mean, you always have a core detector that is your double beta decay detector, that is the one that is counting events here. Whenever the veto see something, in principle should tell to the detector, okay, stop for a while, don't count, because now there is a background outside. Okay, so the first answer is we go underground because vetoes are not efficient above ground. Above ground, you have a problem, okay? Then the second is need a fast detector. The veto has to be fast, because in that case, I mean, the response of the detector is important. The third is that, of course, you can reconstruct the interaction that it's not always needed that you say do not count. I can try to reconstruct the interaction and understand if this interaction could produce a moon. For example, if I have a moon and I see that it's crossing the detector, maybe I decide that in that case I do not want to veto my detector. And then, of course, there you have to put numbers and understand if we call it dead time. I mean, the amount of time in which the veto says to your double beta decay detector, stop for a while, is called the dead time. And the dead time is important. And you need to find a compromise. And of course, this also is stay in the choice of the underground detector. So what I mentioned to you before, for a while we discussed if Gran Sasso was deep enough for, well, we started from dark matter times ago. Is deep enough or in the case of dark matter was exactly the neutron induced by moons that were dangerous because neutrons produce exactly the same signal of the interaction of a WIMP, okay, a nuclear recoil. So there is no way to distinguish between a WIMP signal and the neutron signal. So I have to remove all the possible neutron signals. So we discussed if it was deep enough. And in that case, it's very specific of the experiment. So you need to understand, because each experiment has his own region of interest, we call it, where the signal should appear. It's here or over here in the case of double beta of dark matter. And depending on that, you need to understand. But at present, it looks like we can operate. I must say for Cupid, that is the next step after Cuore. We do not see big problems with the depth. It was discussed for some time for Legend, and Riccardo for sure will discuss this point with you. And I have no idea of next. So. Depend on the interaction that you want to reject. I mean, if it is just a prompt interaction in correlation with the particle that I'm tracking, I can veto. So we say we open a gate, a window in which we do not accept events that has more or less the time response of your detector. You take, I mean, you have to consider either the time response of your double beta decay detector and that of the veto. If you are worried by any kind of delayed coincidence that could be produced because you have excited a nucleus and it takes a while to decay, you may need to open a wider gate. But in that case, for example, you can also put a cut on the energy, because maybe in that kind of process can take place only if the first interaction has a certain energy. And this technique can be used also to reject background coming also from natural radioactivity, because in natural, you know, what are the radioactive chains. So uranium have a decay chain where a number of isotopes are produced through alpha decays or beta decays. And some of the steps are very fast. And so in that case, you can use, for example, an alpha decay to tag. An alpha decay maybe doesn't produce a background in your energy region, in the region of interest, but the next decay is a beta decay that can produce a background there. So you use the information on the alpha decay to open a gate and say, okay, if, but in that case, it's not that I have one trigger. The condition is I have one trigger in correspondence of 5 MeV alpha particle, and then I reduce a lot the rate. Is not the total rate that I am recording, but is much smaller rate in that energy window. And then I see after 10 seconds an event here. In that case, I do not record that. Okay, so there are a lot of techniques in which I can improve my efficiency, namely reduce the time, but they are very specific on the process that I want to avoid in some way, and of the detector and of my region of interest. So the techniques are similar, but really depends on the experiment. So gamma backgrounds are, the background coming from natural radioactivity are not only gammas. You have gammas mainly in this energy region, between threshold and 2.6 MeV, that is the higher line that I have shown in the spectrum here. Okay, this line over here. You see that at higher energy, the background drops a lot, more than 1 order of magnitude. Then I have alphas, those alpha that are dangerous for this, for neutron production. And they have energy between, no, this is not 3, is 4 and 8 MeV more or less. I have betas up to 5 MeV. And there are 2 strategies for their reduction. One is the passive one, I just put shields. And the other is an active one. Try to identify the interactive particle and use time and space correlation as we were discussing. So the point what is that if I want to shield events produced by natural radioactivity in the rock or in the infrastructure of the underground lab, I can use veto or passive material or passive shields. But natural radioactivity is also in my detector, in the holder of my detector. And so I need additional strategies to remove also the interaction due to radioactivity that is in my detector. And one of the strategy is material selections. I just use very, very clean material, radio pure material. And the other is try to identify the particle in some way. So it's, again, this is strongly correlated to the technology that you use for implement the source equal detector approach. So it depends on the kind of detector that I'm using. In general, let's try to understand what changes from my signal that is due to 2 electrons and signal produced by radioactivity. If I have alpha particle, they have a very, very small range, okay? And so they produce in my detector a very small hotspot that is even smaller than the one of double beta decay. So if is really just a dot, okay? Because this is a few millimeters, this is, say, I think I wrote 2 millimeters, And this could be 10 micron. Okay, so it's quite it's a small spot with a high ionization density. Then we have electrons, and electrons are electrons. So either they are electron produced by this decay or by radioactive nucleus. They are the same, so I cannot distinguish. And then we have gammas. And gammas, this is the cross-section of gammas. So you see, this is 1 MeV. So the region where gammas having energies above my region of interest, comparable with my region of interest, is a region where gammas interact with Compton. Then after the interaction, they lose energy, and so they move with Compton, they do not disappear. They just lose a fraction of the energy. So I still have gamma rays. And they disappear when the cross-section, their energy is lower, and the cross-section for photoelectric absorption becomes relevant. Okay? So this is a picture of the differences. This is a muon that is ionizing along the track. And here I forget the other less important processes like neutron formation and so on. Mainly it produces ionization along the track. Here is my double beta decay, the 2 electrons, neutrinoless of 2 neutrino, or in any electron produced by natural chains. But this is, let's call the topology of my event. My candidate event is a hot spot with this dimension. And this, here I mean, the dimension is similar, but should be much smaller. That of an alpha particle is a hot spot, much smaller. While a gamma do something like this. Different hot spot in spread in your detector. And so, you see, if I have a detector that is able to have some kind of tracking capability, I can reject background. And if I don't have tracking, but I have an array of detectors, I can do the same. Muons as gammas interact in more detector, while my candidate decay should involve only one detector. Okay, we are not done. I have 2 slides more. So, technology. Once you have all this information that we collected during this time, you have to choose your technology. And the problem is that there are strong correlation. If you choose the candidate with a group of candidates, you have a small amount of technologies are viable. On the other hand, if you choose the technology, you have a small amount of candidates. You see, if I choose a semiconductor technology, do you know which are the candidates that I can explore in this approach? Germanium for sure. Cadmium. And tellurium. Because it's a there are cadmium telluride semiconductors. However, these semiconductors, have good performances only when they are very small. And so they are not competitive, and only germanium is competitive. Okay, so this is just an example. If I choose xenon, I cannot choose a technology, the technology of semiconductors. Okay? I could choose a scintillator, and in that case, I will have a lot of technologies, because xenon is a scintillator, but I have also cadmium tungstate, that is a solid state scintillators, and so on. And the same is for the background. Once I have chosen technology and candidates, I have a kind of special kind of backgrounds that are particularly dangerous. And once I have chosen the technology, I have only a subset of active rejection techniques that can be used. So just to show you two possibilities. In one case, I can have an array of solid-state detectors. Just look on to few information that are in the next slide. I think these are information on the experiment, but I can choose a solid-state technology, or I can choose the Kamlan-Zen technology, that is that of liquid scintillator. Which are the differences? Well, one of the big differences is the energy resolution of the detector. I have 5 kV here and 200 kV here. Okay, you see what is the difference? One is like this, and the other is like this. Okay, so if I have to claim that I've seen a double beta decay, I have to convince the community that my events are not due to some kind of radioactivity, maybe a very rare decay that is not have not been yet observed. And of course, the probability that you have a background line in 5 kV is quite different than having it in 200 kV. However, if I want to scale the mass, here I just have to, it's not exactly like this, but I mean, a balloon a bit larger. Here I have to change my cryostat. Yeah, okay, so yes, I go. When you choose the region of interest, you want a region where for sure all the candidate events, I mean, when you record your events, you have an energy resolution. And so the response of your detector to a double beta decay is generally are Gaussian-like. The response of detector is a Gaussian. The width of this Gaussian is the energy resolution of this detector by definition, okay? Generally, you study an energy region that maybe is twice the full width, it depends. But what you require is that a high fraction of your double beta decay events should stay in that region. So say 90%, something like that. So the energy resolution, okay, you know that this is in a Gaussian, we are used to talk of, to say the truth, this is, I mean, the full weight of maximum of a Gaussian is nearly 2.35 sigmas, okay? So if you look at papers, you discover that All high energy resolution detector quote the full width, the other quote the sigma. But in any case, I made the translation. So, but I mean, in a sigma, you have only 68% of the events, and you do not want to lose 23%. And you remember, the time scale is 10 years, 2% of 32% of 10 years is a quite long time. So you prefer to accept some more some more events and choose a 90% or more than 90% energy window. So that is the region where you search for the decay, okay? So, I mean, you have an advantage from the point of view of high resolution detectors, but the price generally is that scaling with mass is difficult. Okay? And I show this and then I close here, even if the sensitivity we will discuss one of the next days. So just to show you the difference. This is the background, I mean, the physics data, we call it background because it's populated by background events and we have not yet seen any neutrinoless decay. This is the background, the physics data collected by Core experiment, a bit more than 5 keV energy resolution. And this line is the region of interest, okay? Where this is, the candidate is tellurium 130, and the line should appear here with the width of this same line that you see here. This is the same for Kamlanzen, and the signal should be here. So you see, in this spectrum, there are all the lines that you see here. You just have no resolution to see them, but they are there. Okay, there is also a different efficiency, but the gamma lines are there. You are not able to see them. So you understand how difficult it is to extract a signal from this spectrum, and is just a deformation of the continuum that you see, while in that case you should see really a line. Okay, so this is the advantage of high resolution detectors. Of course, if you, now the future, the experiment that we want to build, what we want to reach is a region of interest where no background appears in 10 years. And so it's challenging to have no background in 5 keV. It's much more challenging to have no background in 200 keV. Okay, so this is exactly what I've told you. Okay, I don't want to go on evaluate the sensitivity and compare competitors because more or less we have discussed this. Sensitivity will depend on the mass of my source, on the time that I wait for the signal, on the background that can spoil my signal, and on the energy resolution. So I've already told you what are the ingredients. The sensitivity, which is measured as the maximum half-life that with my experiment is that my experiment is able to achieve, can be written in these two formula depending on the condition that is called here zero background. That means no event in the region of interest during my exposure, my data collection. Look at these two formulas and try to demonstrate them. It's quite simple. It's just a statistical, all the information are there. There are two approximations. The green line is the best solution because if I have zero background, my sensitivity scales with mass and time. If I have background, it scales as a square root of mass and time. And this means, this is of course written as, if I don't see a decay, I put an upper limit on the half-life, okay? And this is the maximum upper limit that I can put with my experiment, given the condition on mass, time, my 10 years, background, and energy resolution. And so now you have all the ingredients. This we will. You can draw the cost budget, but Giovanni, I was forbidden to. Giuseppe told me, no, do not go ahead with the cost budget. No, I don't have. Have you any idea? You're too young, but maybe. I mean, no, it is meaningless because, I mean, you always need the scale of the problem. So you should be able to compare with other projects, with other fields, and understand what are the differences. So if we compare with biophysics, for sure, we are extremely expensive. If we compare with accelerator, we are extremely cheap. And therefore, the glass can be half empty or half full as you like. But this is the answer to the question that was asked from, I don't remember who of you, why don't we explore the full range of the Majorana mass? There are two answers. On one side, because it's difficult. It's already technically difficult to build a 1-ton experiment. If we want to go, I mean, to look at 10-ton, 100-ton, we have to improve our technologies. We have to understand better how to reduce the background. Maybe we need to go deep. I mean, you understand, we cannot play only with the mass. We have also to play with the background, at least to guarantee that we have zero background. And then there is the cost. And the cost is not only because we have to buy the isotope. That is a nightmare, but also the human resources to construct an experiment. So, and in any case, the other point is that as in all fields, you need to go step by step. You cannot have a small prototype and then say, okay, now I have 1 kilogram prototype and then I scale to 1 ton without intermediate step. The history told us that all the experiments that have tried to scale from a very small to a huge lose the competition. So all the experiments that are in the field since 30, 40 years are going step by step, and each step is scales the sensitivity by about 1 order of magnitude, more or less. And then you discover something new. For example, from the point of view of background, because 20 years ago, some of the backgrounds that I discussed, we didn't even ever thought that they could be dangerous. And so you have to learn in your step approach and then implement what you have learned. Okay, I'm sorry, I was quite long. I hope you can, okay. The choice of material for the source. No, the problem is you cannot tell this. No, absolutely, because it's not only candidate dependent. So your question is, from the point of view of the choice of the candidates, which one can have the best signal to background ratio? Yeah, the problem is that in any case it depends not only on the candidate but also on the technology that you are using, and well, on the energy. So because the technology defines. As Maura was saying, it's always the background in the finest being that you can consider to evaluate S and B compared to the resolution, which you can afford to define because of your energy resolution. So, for example, in Cameron Zen, you could imagine you had 10 different liquids that you could fit, but if the resolution is always of the same, more or less the same type, and the Q value of the 2 beta changes for the liquids, so the atoms, you still are limited by the resolution. So that. No, I mean, if you just want to understand if you are considering as background only the 2 neutrino process, you can fix a ratio. Well, it depends. And there you have all the information, because you do not need exactly to have the shape. I mean, the shape can be evaluated, but you do not need exactly the shape of this tail to understand how many counts you have in this energy region. You have more or less the shape. You have, for almost all the isotopes that are of interest, you have the half-life, and so you know that for all the one that we are studying within the next generation, I don't know I'm not able to say when we want to go beyond the inverted ordering, but for all the isotope that we are considering now, the 2 neutrino double beta decay is not an issue, but for a case that I will discuss with you, because the case of Cupid I will discuss with you in 2 days from now, but it's not that tail. So in most cases, for example, for xenon, there are next generation experiments that are planned, and they do not have an important contribution from the 2 neutrino. So we still, on the other way around, with the exception of the case that I will discuss with you, all the other experiments that are facing the construction of a new phase, more powerful experiment to fully explore the inverted hierarchy region, so achieve the 20 millielectron volt on the Majorana mass parameter, the 2 neutrino double beta decay is not an issue. They are still at the level that the problem is the other sources of the ground. We would like to achieve that point. And then when we will be closer to that point, of course, the energy resolution will be the key. Yes, but we still have to to work a bit for that. For the half-life of two neutrinos? Well, what happens is that all the running experiments that are using those isotopes, not all of them, but most of the isotopes that I discussed, they are able to measure the two neutrino double beta decay. So it's the one on Wikipedia is a bit, it's old, not that much, but it's not so updated, but you can find in literature. And for germanium is measured by Gerda, and for tellurium is measured by Cuore. For molybdenum was measured both by Nemo Frey experiment, that is the experiment with the foils that I described you, and is measured also by Cupid Mo, that is a bolometric experiment. So it's not that old. I mean, on Wikipedia you may, but you find also historical measurement on isotopes that are no more considered. But for all the isotopes that are now considered, is very well known. I don't think so, because at the end, I mean, it's not easy to define exactly what are the priorities when you choose a candidate, but I would say that having a high Q value is a primary need, because you gain in phase space, and you gain in background, because your signal, this peak is in the high energy part of the spectrum, and whatever is your background has always this kind of shape. And so there we have identified the candidates, and they are more or less the one that I've shown you. And the other point is that you have the need of enrichment. Only for tellurium, you can do with the natural tellurium, because the isotopic abundance is above 30%. All the other cases, you understand why we need enrichment. If this source material contains, is not enriched, instead of 1 ton, my source has to be 10 tons, much higher. And for sure, I will lose in efficiency. There is one point I did not discuss, that is the detection efficiency. So the probability that if a double beta decay takes place, I record an event here. Since in data acquisition, in detection, data acquisition, and so on, I have possibility of losing events for a number of reasons. The efficiency is important. If I have a lot of additional material, for sure my efficiency goes down. So more or less, the candidates that will be explored in the next 10, 100 years, I don't know, will be those that we have already, that we are considering now. And then the other, what will define the choice is more or less the technology that you want to use. Do you have other questions?
General one. So currently, which is the best
Okay, I try to, maybe I have also one slide. So what is the present situation? The present situation is that okay, if you want a full list of double beta decay experiment, it's huge. But of course, those that are very sensitive. We compare them on the Majorana mass parameter. They are few. And I have a plot somewhere here. Not this one. Let me see if I have a better one. No. Okay, I can use this one. Okay, so this is the plot that I've shown you, the Majorana mass versus the lightest neutrino mass, one of the free eigenstates. And the allowed region are this band, these two bands that correspond to what I call inverted and the normal ordering. And these two bands are here. So present experiment are these fillet bars here. These are the results. And so we have a xenon experiment. These two in red are experiments done with germanium. Then we have EXO that is uses xenon. Then we have the other that are running, for example, is Cuore that uses tellurium. And these are the futures. So what we are doing is the following. We have few experiments that are still running and taking data. And we already have plans for their upgrade to, let's say, the ton scale. And this requires money and improvement of the technology. From the point of view of the technology, the real challenge is to be able to have a reliable prediction of the background. Why? Because mainly we are dominated by internal background of the detector for radioactivity and so on, and we do not have tools to measure radioactivity of materials with that sensitivity. The experiments measure the radioactivity in a better way than can do any kind of independent technique, such as gamma spectroscopy and so on. So we use the running experiment to measure the contamination of the materials and try to understand what are the important contributions, work on their reduction, and prepare for the next stage. So there are a number of experiments. There are 3 big experiments that are under discussion in between Europe and the States. They have a proposal, and part of the construction is already in progress, at least for 2 of them, I would say. And one in Japan. In that case, I think they do not have problem of funds. And while the 3 in between the States and Europe are also waiting for funding agency official commitment. So the community are working on the project, and they are, the strategy is to increase the mass and to reduce the background. So increasing the mass is just money. Technologically, is not that difficult. 2 of these experiments need a new infrastructure. So let's say the cryostat in which they will work, they are completely different, but in any case, they need a cryostat and Eveto in the case of Legend, or a millikelvin cryostat for Cupid. And, sorry, the two that need a new infrastructure are the one using Xenon, that is Nexo, and Legend. And they need a completely new infrastructure. The other that is Cupid will use the infrastructure of Quore. But beside this, I mean, increasing the amount of detector material is more a problem of, I would say, of funds and work than a really technological issue. While what is really from the scientific point of view, the problem is to have the ground under control. That is the side. And the other strategy is to convince the funding agency that, that they have to fund us. That is why I'm not discussing the budget profile. But of course, this is what I mean, once the experiment have gone through my list, and they have done, now they have a project. So all the list of choice, from the choice of the candidates to the different technologies that I want to use are defined. And now we have defined over also our funding, our budget, and we have to wait for that for approval. But this runs in parallel with a lot of activities. So at least for both Legend and Cupid, so the dual experiment that will be in Gran Sasso. It's completely different for Nexo, because the predecessor is closed since a lot of time. So in that case, it's a bit different. Then we have also an experiment that is next, that is not still at close to the 1 ton stage, is really challenging from the point of view, technological point of view. It sits in the middle between high energy resolution and low energy resolution experiment. And JJ will come and discuss in the next week. Will illustrate you the experiment. So that is more or less the international situation.
Maura today had the challenging task of trying to introduce you to various issues and how from zero we can get to an ideal conceptual design. But then the main techniques which map either those with and incarnating different readout techniques, readout types of detectors, will be discussed for the rest of the school. So she will focus on bolometers, and so what she mentioned to be, let's say, the core equipment approach, contemporary approach. And next week you will have Ricardo for the Venus, the Legend approach, and JJ for the Xenon approach, which will be both Nexo, and
Xenon, yes. Oh, yes, it's quite. No, you're asking why it's easier to investigate. Simply. Yeah, it's simply because this parameter has a higher value, and this parameters defines the half-life. So if, I mean, if this parameter has in nature has a value that is in this region, neutrinoless double beta decay is faster. And it's easier to detect simply because I have more events.
So basically this parameter not only dependent from the delta m squared, but also from the sign of the delta m squared?
Yeah, yes, inverted, and you mean the delta m square of the, yes, because the inverted ordering and the normal ordering are defined by the sign, yes, of the delta m square.
Then do the 1, 2, 3 as she was showing, and you constrain those 1, 2, and 3s with the delta m squared that you measure, and then you do the sum of these 1, 2, 3s, you see that one is like this and the other one is like this, and so the lightest, so summing this one, which is more in this situation, gives you that situation, that split.
Okay? Thanks.